Hello students, our today's topic will be an example on flexural members. I hope you have gone through the theory parts, uh, what I have suggested earlier. The In numerical, we can design the flexural member of any kind of steel member we can design, and we have to follow the clause number 8 of IS 800. And on in that clause that is given, there are two type of method we can do. That is, one is lateral, if the beam, two type of conditions are there. If the beam is supported laterally, or uh, the beam is not supported laterally, right? So first of all, we will be considering the laterally supported beams, and this is given in clause number 8.2, laterally supported beams. And in clause number 8.2, you can see that in laterally supported beams there are two conditions. One, if the case is low shear condition, and one if the case is high shear condition. How we can find out? If the shear force, the acting shear force is lesser than zero point 0.6 of design shear strength, then we can say that the case is low shear case. And if this is not, if this exceed the zero point 0.6 of VD value, then we have to say this is high shear case. So for low shear case, we have done all the things. That is, we can find out the design bending strength by this formula in clause number 8.2.1.2. All the details are given over there. And if the case is the high shear case, for high shear case also, we can say that there are two cases. One, if the section is plastic or compact section, or if the section is semi compact section. So two cases are there for plastic and compact section. This is given in clause number 9.2.2, that is, mdv will be equals to this equation. This is given in this clause. And dv value we can find out from this clause 8.4.1, 8.4.2, right? And the other case is semi compacted section, and this is we can find out in clause number 9.2.2. Those things we can find out. And what will be the value of uh, decision shear strength? That this would be v equals to v should be lesser than the vn divided by gamma m0, and vn is the nominal shear strength, which will be equals to shear area multiplied by fy of the wave, and root over divided by root over 3. And this we can find out in clause number 8.4.1, right? So those things we can find out in various clauses, and uh, we can get those equations. Now, how to solve any example, right? Let us consider one example, and try to solve it, right? So one example is there, that is, they are saying, suppose a simply supported steel joist is a type of beam. So steel joist of 4 meter length, right? Effective span, 4 meter of effective span, and is laterally supported. So this condition is laterally supported condition. This is okay. So we have to consider only those two cases, and we have to see whether the case is low shear case or the high shear case. So we are not taking any example right now about the unsupported one, right? So laterally supported beam, and it carries a total uniformly distributed load of 40 kilonewton. Total load is 40 kilonewton, 40 kilonewton, right? Total UD load, and it is including the self weight also, right? So those are the cases they have said, and they have said that design appropriate section using steel of grade FE 410. They have said those things, right? And you have to design this. Now how we can design it? So let's design it taking various steps. So suppose step number 1, those are the given data we have already seen. What will be the given data, right? For FE 410, take the given data, that is Fy for this case will be 250 MPa, and Fu will be equals to if YW will be equals to, that is the Fy of wave, that we need this thing in future. So this will be again equals to 250, as because all the values wave and plane will be same. So those are the values we can get. Now take the first step, that is step number 1. If we consider step number 1, in step 1 what we can do, we can find out the load and moment and shear force, maximum bending moment and maximum shear forces, right? So what is the load given? The load is given, that is total uniformly distributed service load, right? This is given uniformly distributed service load. This is in total, that is 40 kilonewton. This is given. So what will be the factored load? Factored load will be equals to 1.5 times of 40 kilonewton, that we actually already know, right? So this will be 60 kilonewton. Find this. In step number 2, what we can do, we can find out the maximum bending moment and maximum shear force of this beam. So this is simply supported beam having UDL throughout the length. So maximum bending moment will be WL square by 8, right? So WL square by 8, we can split it WL into L by 8, and WL is a total weight. Now it is total weight, in this case total weight is given, so WL, this will be in 60, right? 60 multiplied by the length, that is 4 divided by 8, so this will be 30 kilonewton meter, and shear force, maximum shear force for this case will be WL by 2, this is 60 by 2, that is 30 kilonewton, right? In step number 3, what we can do, in step number 3, as because we have to design this, in step number 3, first of all we have to choose one section, right? So step number 3, try to find one guideline from which we can choose a section. What will be the guideline? We can find out the ZP required, right? The ZP required, we can find out this required ZP, we can find out from the formula, that is M divided by Fy by gamma M0, right? So the M value we know, that is 30 kilonewton, already find out on this one. So this is 30 divided by Fy 250 divided by 1.1, so this is coming 132.10 to 132 multiplied by 10 to the power 3, this is in mm cube, right? This is coming. So this is our guideline. We have to take one section which will be having the ZP value greater than this at least, right? So this will be our guideline. So in step 4, we can choose one section, right? And for beam, we know that is the suitable section is I section. So suppose we are taking ISLB 200, we are taking. suppose we're taking ISLB 200 at the rate 194.2 Newton per meter. For this case, the value of ZP is equals to 184.34 multiplied by 10 to the power 3 mm cube. So we can say this Z is greater than our ZP required. So obviously we can consider this section. So now let us find out all the properties, geometrical properties of this section. Those are the depth. Total depth D is equals to 200 millimeter. BF, that is breadth of the flange, is 100 mm. TF, thickness of the flange, is 7.3 mm. TW is equals to thickness of the wave is equals to 5.4 mm. Radius of root radius, that is 9.5 mm, right? And obviously the depth, suppose we need to find out the depth of wave only, so depth of wave will be equals to the total depth of the wave will be equals to, suppose this is the I section, so this will be equals to the total depth minus this thickness of the flange minus this root radius up to there, right? So this will be equals to total depth minus 2 into S, because this will be in both the sides, so 2 into thickness of the flange plus root radius. So this will give, if you put all the values of those, this will give you the value 166.4 mm, right? And other properties such as the IZ is equals to, for this case, is equals to 1696.6 10 to the power 4 mm to the power 4, and ZEZ, elastic section modulus, this is plastic section modulus, this is elastic section modulus. ZEZ is equals to 169.70 into 10 to the power 3 mm cube. So those are the properties you can find out. This you can find out in SP6, and this value you will not get in SP6. This you can find out from your IS code 800, right? So if this as because in IS code IS 800 the sections are limited, so if you choose any kind of section which is not in IS code, you have to find out the value of ZP. And how to find out the ZP, either you can find out in internet, or I will tell you, or I will do some workout example on ZP later, right? So those are the things we can find out, all the things we have written, right? In step number 6 sorry, in step number 5, what we can do, we can classify the section. What will be the section classification? So how to do that? This you will this classification you will get in table number 2 in your IS code 800. How to classify that? First of all, let us find out the epsilon value. The epsilon value in this beyond this table, below this table you can see this epsilon value is equals to root over 250 divided by Fy. In this case the Fy value is 250, so this will be 250 by 250, so you will get 1. So epsilon value is 1. To find out the classes of this section, you have to find out two ratios, that is B by TF, this ratio, and D by TW, this ratio. What is B? If this is our section, if this is our section, so this is the breadth of the flange BF. B will be half of this, right? Send up to the center of from this. So B will be equals to BF divided by 2. BF is equals to 100 in our case, so this will be 50 millimeter. So B is known. Now small d, we have already found out the small d value, that is width of depth of the web. So and TF TW we have already know, those things, so we can find out those two ratios. This and these values are coming, here. 6 point, let us do in this manner. B by TF, this is coming 6.849, and D by TW, this is coming 30.81. Now you can easily see this is lesser than 9.4 and this is lesser than 84, right? So if this value is lesser than this and this value is lesser than 84, we can say this section is plastic section. So you will get this in table number 2, right? So we can say from the table number 2 this section is plastic section, right? So this is over. Now again we can see that this ratio, that is depth by thickness ratio of the web, this is equals to 30.81, which is again lesser than 69 epsilon s, because epsilon value is 1, so this value is lesser than 67. If this condition occurs, then we don't have to check the buckling for web, right? So buckling check for web, buckling check for web will not be required, right? Will not be required. Okay, so in step number 6, what we can do, we can find out the shear capacity, right? The design shear capacity. In step number 6, we can find out the design shear capacity. How to find out this design shear capacity? This design shear capacity VD is equals to Fy divided by √3 by gamma m0 into the shear area, that is depth multiplied by total depth multiplied by the thickness of the web. This equation you will get in clause number 8.4, right? This you will get in clause number 8.4. So if you put all the values, if all the things are known right now, Fy, gamma m0, capital D, TW, those are known. So if you put the values, you will get this value as 141.713 in kilonewton, right? In kilonewton. You have to put all the values and convert it in kilonewton, so that you will get this value. This value, you can see that this value is greater than 30 kilonewton. What is 30 kilonewton? 30 kilonewton is our maximum shear stress, which is due to the applied load, right? So we can say design shear strength is greater, so hence this is okay, right? So we can go forward with assuming the same section. If this not satisfied, so we have to change our section, and we have to change our choose one new section, and we have to do all the steps, right? Okay, now look at the next step. Next step is will be step number 7, right? Step number 7, we have to see that what will be the condition. Earlier I have already told you that there may be two cases with which we have to design. One case is high shear condition, one is low shear condition. So first of all, we need to know whether this is high shear condition or low shear condition. So what is the condition was there? What was the condition? That is the shear value is either will be lesser or greater than shear value is whether this shear value is lesser or greater than the 0.6 of Vd, right? Now look at what will be the value of 0.6 of Vd. 0.6 of Vd will be equals to 0.6 or Vd already we have find out in the last step. So this is equals to nothing but 0.6 multiplied by 141.713, right? So this is 85.02 kilonewton, right? And this value is greater than the 30 kilonewton, that is the applied maximum shear force. So if this is greater than this 0.6 Vd is greater than V, we can say this condition is low shear condition, right? The condition is low shear condition. So we have to design all the next parts using the formula for the low shear condition. So in step number 8, we can check the design bending strength, right? Design bending strength, that is MD. And for low shear condition, what will be the value of design bending strength? This will be beta V ZPZ Fy by gamma m0, right? What are the values of beta b? Beta b values are given in the code, and the clause number this you will get in clause number 8.2.1.2. so in this clause all the values of beta b are given. For plastic section, as because this section we have already found out the classification section is plastic, so for plastic section the value of beta b is 1 for plastic section, right? ZPZ already known, Fy value already known, gamma m0 value already known. So if we put all the values, we can find out the value of MD. This is coming 41.895 kilonewton, and you have to convert, obviously we have to convert in kilonewton meter, so you will be getting this value, right? So there are some limitation in clause number 8.2.1.2. you will be getting this MD value has a limitation for simply supported beam and for cantilever beam. Two different cases are there, and for simply supported beam you have to check whether this value is greater than or lesser than this value, that is 1.2 ZE Fy divided by gamma m0. All the values are known. ZE you have already seen this value. Fy value is already known. So if you put all the values this and convert this in kilonewton meter, you will be getting 46.28 kilonewton meter. Now if you compare these two values, you can see this one is the lesser one, so this is satisfying the limitation. So obviously we can take this value MD value as this one. So our MD value will be 41.895 kilonewton meter, right? Kilonewton meter. So this we can take, right? Now this is the design bending strength. What was our bending maximum bending moment? This was coming, maximum bending moment was coming. Our maximum bending moment was in this case our maximum bending moment was 30 kilonewton meter, right? So our this value is greater than 30 kilonewton meter. Yes, so our design bending strength is greater than our design bending moment, which was occurring or generating due to the load. So we can say this section is okay. Till now it is okay, right? So if this section satisfied the previous one but not satisfied this section or this segment, again you have to choose a new section and you have to do all the parts, right? Now in next step number 9, in step 9 we can check for deflection, right? This check you can do using the table number 6 given in your IS code, IS 800. According to this table, the permissible deflection is delta. If suppose this is delta, this deflection is limited to L divided by 300. What is the value of L? L is 4, right? If you convert this will give you in millimeter this, so you will be getting the value as 13.13 millimeter. So according to table number 6 of IS code, the permissible deflection is this, right? Now let us see what is the maximum deflection coming. The maximum deflection for any simply supported beam having UDL of W, this maximum deflection is equals to deflection delta max is equals to 5 W L to the power 4 divided by 384 EI, right? Now as because total load is given, so we have to split it again. So suppose that splitting this is W into L to the power 3, right? Now you can see all the values are known. This is W into L. Now one thing there you should remember, that in this case you have to take the service load, not the factored load, right? You have to take the service load. What was the value of service load? The service load value was 40 kilonewton, right? Total load. So this WL will be equals to 40 kilonewton, not 60 kilonewton, as because this deflection you have to use, this will be in this deflection will be under service load. So you have to take the service load instead of factored load. So if you put all the values, other values are known, right? EI, all the values are known. If you put all the values, this delta max, this value is coming 9.82 millimeter. So you can see this is lesser than 13.13 millimeter, as because this was our limitation. So this is beyond limitation, so obviously we can say this is okay. Again, if this check for deflection is not working, if the deflection is coming higher than this value, we have to again design using different section, right? So after this there can be two checks. One is uh, wave for wave buckling, another one is for wave crippling. Now, as because we have already seen that this value that this value is d by tw value is lesser than 67, so buckling check is not necessary, but we need to do the crippling check. So for wave crippling we have to check, right? For wave crippling we can find out the bearing strength. For wave crippling, check for wave crippling, the bearing strength will be equals to Fw will be equals to P plus N2 divided by Tw Fyw divided by gamma m0. Getting the formula, right, for wave crippling, they have assumed that any kind of concentrated load or any kind of reaction will be dispersed into the wave with a slope of 1 is to 2.5. 1 is to 2.5. That means if a concentrated load is coming, if this is the bearing, right, having the width of b, so this will be dispersed in the ratio of 1 is to 2.5, right? So if this is b, and this will dispersed at a length of at the root radius, at the thickness of root radius. So at root radius what will be the distance? This will be tf plus r1, as because tf is the thickness of the wave, thickness of the flange, plus this will be the radius of the root r1, so this will be tf plus r1, right? So this value, the n1, if this value is n1 and this value is b, the n1 value is will be equals to 2.5 of tf plus r1, b1 will be equals to b plus 2 and 1 in, so this is the value of b1, and how the formula for this strength is equals to b1 into tw multiplied by fyw divided by gamma m0. So if you put the value of b1, you will be getting the equation. Here I have written this in n2 instead of n1. You can write n1 also, whatever. So this value we can find out if this n2 value will be equals to 2.5 into tf plus r1, as I have already told you. So this value, after putting all the values tf and r1, those values are known. If you put the values, this will become 42 millimeter, right? Then suppose we are assuming bearing is equals to 75 millimeter, bearing of 75 millimeter. Assuming this value and finding this value, put all the values, all the values are known. If you put the values, you will be getting this fw value is equals to 143.59 millimeter. Now this is the strength, and this is way more than this value. What is this? This is a maximum shear force, so there is no chance to fail in crippling uh, with the maximum shear value of this. So this is again okay with respect to the shear crippling, right? So this is how we have to design step by step, was given to you. So this is one example for low shear case. You can do this with high shear case. If possible, I will do another example for high shear case also. Thank you.